Hello and welcome back. In this session, we'll go through 6 most fundamental pillars, also known as core components of any system design. Over the last 2 decades, large-scale web applications have made a lot of progress. If you see the social media giant like Facebook, Instagram, Twitter, Google, and all the apps and services that we use every day are highly scalable in systems, right? So since billions of people around the globe access these systems, at the same time, they need to be built to handle large amount of traffic and high volume of data. This is where a system design comes to play. Introduction to the system design, what exactly the system design is, and we'll talk about the pillars of system design. That's also known as usual, like different core components to consider when anyone is really jumping into any of the system design. Design is not just what it looks like and feels like. Design is how it works. So on that note, let's talk about what is system design. As a software developer and engineer professional, you are increasingly expected to understand the concept of system design and its applications. In the early stages of your career, learning system design will help you tackle software design issues with confidence and apply design principles to your day-to-day work. So as you extend your career, that is one of the most important criteria to be in that particular position. Therefore, system design is very important regardless of any level. As the system design grows exponentially, this session of discussion will help to understand the system design. This is most fundamental core components of any system design and details. So what exactly the meaning of any system design? Right? System design is a process of defining the architecture, interfaces, and data of a system that meets specific requirement. It is to build a consistent and efficient system. Once the requirements are finalized, it can be mapped to a physical system design that meets all the needs for your system design you are trying to build. How you design your system depends on whether you use customized development, e-commerce solutions, or a hybrid solution. Right? So system design requires a systematic approach to design and build a system. A good system design requires you to think about everything in your infrastructure, starting from hardware and software to data and how it's stored. Pick any product in the market and analyze. You will find a beautiful system that helps to build the complete product. To build any large-scale system, it needs a very well-thought design and architecture. So for every system design consists of very fundamental core components. Those I call as the pillars of the system design. Without those, no system can be established. So here are the pillars of any system design. So what are the core components, what we call as pillars of any system design? Starting from there is load balancer. So load balancer is nothing but a piece of hardware, or you can say a virtual hardware that acts like a reverse proxy to distribute network and or application traffics across different servers, right? So that's what we call like load balancer. And there is another component called a cache is a special storage space for temporary files that makes a device, browser, or app to run faster and more efficiently. The third one is, would say, storage or data storage. Data storage refers to the use of recording media to retain data using computer or any other devices. The most prevalent forms of data storage are file storage, block storage, and object storage. There are also there is another storage, we'll talk about that later, with each being ideal for different purposes or different use cases. The fourth one, which is like it's API. So API, it stands for Application Programming Interface, right? And API is a reliable way for two or more programs to cooperate each other. It allows programs to work together despite difference in hardware, language, architecture, or any other operation constraints. So the fifth one is message queue. It's a queue of messages sent between applications. It includes a sequence of work objects that are waiting to be processed. A message is the data transported between the sender and the receiver in two different ends, and it's essentially a byte array with some headers on top. And if you say some example of example of a message could be an event. And the last but not the least, there is a security. So the security, it's by design, is an approach to software and hardware development that seeks to make system as free of vulnerabilities. So security has to be all over the system when you are designing any of the system or any of the product. So that's very basic component for and very fundamental component for any system design. Let's take a deeper look into the load balancer. In a nutshell, a load balancer is a piece of hardware, or as we said, or a virtual hardware that acts like a reverse proxy to distribute network or application traffic across different servers, right? That's what the definition we have already talked about. In other words, we can say load balancer means efficiently distributing the network traffic across multiple machines to balance out the load and prevent any hotspots, correct? It also keeps track of the servers which are not functioning and blacklists those machines, right? So it keeps sending the hardware to the blacklisted servers time to time. If the load balancer gets the heartbeat response, then it starts serving the request to those servers as well. Okay. And also, whenever any server comes back off or new servers are added to the system, load balancer automatically resumes the traffic distribution to that server again. Try to imagine what a system look like without a load balancer. So in this picture, if you notice, it's a high level system in which the client request directly hit to the application server and so on, right? In this kind of design, we can see two major problems. One is single point of failure, which really leads to whole system collapse in the event of any server failure, and no request will be served if any of the component fail. The other one is overloaded server, right? Which means a single server has to process all the requests and response accordingly. And however, if there are high demand in the product and all of a sudden the users increase exponentially, then the server will be overloaded with a pile of requests, and back pressure will be increased, and then system latency will be degraded, right? So that will be another biggest problem when we are going with a very traditional way of designing a system where there is no load balancer available. If we add a load balancer into the system, how it really works, let's see. So in this particular picture, if you notice, we have added a new component to our system called the load balancer. So that's placed between the user and the application server, right? And you may also notice we have increased the number of servers from 1 to 4, right? So that means now if one server goes down, there are other 3 servers available to serve the user request, and there are more servers can be added to the application server group on demand to get the better performance, correct? Which is also called the scaling of a system that we'll discuss later point of time. What a load balancer mainly does behind the scene, it manages the flow of information between the server and an endpoint device. It moves the request and response efficiently, optimizes the use of application delivery and data resources, and prevents server loads as well. It conducts continuous health check on servers to ensure they can handle requests. So some more functionality of a load balancers like directing traffic based on data from network and transport layer protocol, such as IP addresses and TCP port, and adding context switching between the server to balance the load, and also applies the routing mechanism based on the attributes like HTTP header, URI, SSL session ID, and HTML form data, which will really help to identify a particular server where the request is supposed to be sent to. There are mainly two types of load balancer. The first type of load balancer is called it's a hardware-based load balancer. They are typically high-performance appliances capable of securely processing multiple gigabytes of traffic from various types of applications. These appliances may also contain built-in virtualization capabilities, which consolidate numerous virtual load balancer instances on the same hardware, where that allows for more flexible multi-tenant architectures and full isolation of tenants, among other benefits. And the other type is software-based. It can fully replace load balancing hardware while delivering analogous functionalities and superior flexibility. It may run on common hypervisors in containers or Linux processes with minimal overhead on bare metal servers. This kind of load balancer is highly configurable depending on the use cases and technical requirements. It can also save space and reduce hardware expenditures, and the cloud vendors can easily handle fault tolerance and elasticity for the users. So these are two main type of load balancer in the marketplace. Right? Load balancer has to identify a particular application server or downstream server to send the request, process the user request. So when we are talking about all these jargon words like context switching, header validation, request distribution, so what does it really mean? So it's all about how a load balancer works under the hood. So it's important to understand the different kind of mechanisms or algorithms used by any load balancer to identify a specific server out of a group of servers to determine how the requests are distributed across the servers. A load balancer follows one of the following algorithms to determine how the requests are distributed across the server. The first one is the round robin algorithm. So this is a very simple technique for making sure that a virtual server forwards each client request to a different server based on a rotating list. It's easy for load balancer to implement, but doesn't take into account the load already on the server. There is a high probability or high possibility of the server getting overloaded with multiple requests if the server is very much process intensive. Other algorithm is called least connection method. In contrast to the round robin algorithm, which doesn't account for the current load on the server, the least connection method does such evaluations, and as a result, it usually delivers better performance. The load balancer that uses this algorithm serves the request to the server that is least loaded at that particular point comparing to the other server loads. Third kind of algorithm used by the load balancer is a least response time method. This least response time method is more sophisticated than the least connection method. The least response time method usually relies on the time taken by a server to respond to a health monitoring request. So the speed of the response is an indicator of how much the server is loaded and the overall expected user experience. So some load balancers takes the number of active connections on each server into account to determine the request sent to each server. Fourth algorithm is least bandwidth method. So that is a relatively simple algorithm as well. It looks for the server that currently serving the least amount of traffic as measured in megabytes per second. Similarly, the least packets method selects the server that has received the fewest packets in a given time period. And the other one is the hashing method. The hashing method is one kind of category make decisions based on a hash of various data from the incoming packets. So this includes connection or header information such as secure destination, IP address, port number, URL, or domain name. There is another algorithm also being used by the load balancers. It's called the custom method, right? So the custom load, I would say. So the custom load method enables the load balancer to query the load on individual servers via SNMP. Right? The administrator can define the server load of the interest to query. That kind of queries would include like CPU usage, memory, and response time. So till now we know like what is load balancer, what it does, how it works, and what kind of load balancer are there, right? So now we'll discuss what are the places a load balancer can be placed in a system design horizon. What are the places you can add the load balancer to make your system performant. So a load balancer can be placed user and the web server, and the other places would be between the web server and the application server, and also between the application server and database server, correct? So these are the places where we can place the load balancer to make the whole system more performant and low latency. So if you ask, adding load balancer in all these places is not mandatory, and of course it depends on the type of system one is building, right? However, doing so can increase the system performance drastically. So the next is cache. So the caching is another pillar and a core component for any system design, okay? So before going deep into the cache, so let's discuss about a real life use case. So have you ever been an extreme low internet connection or no internet connection at all while using any heavy application on your phone or computer? If so, you might have find this kind of thing happen to you as well. So browsing a website first time in a poor internet connectivity or less network bandwidth, often the text is loaded before any high quality image. However, in all other subsequent visit to the same website, the page rendering occurs super fast. Okay, so it's all about the magic of caching. If you see in the screen itself, so there is one of here is one of the demo accessing the Facebook videos in slow internet connection. Okay? So if you notice, the text data and the placeholders are displayed, whereas the actual video not yet displayed, right, and not yet rendered. So so it's important to it's important to deliver the best experience to the user to improve retention. And in today's competitive world, of course, business get impacted due to the poor user experience. Imagine you are watching your favorite TV series on Netflix, but the video keeps buffering, right? Would you really stick around and continue the subscription on that? No way, right? So hence caching plays a crucial role in such cases, right? The caching works on the principle of locality of reference. Cache acts as a local store for the data to speed up the lookup and retrievals, right? So the primary goal of a cache is to reduce the read latency and amplify the throughput of any application or server. Let's take a deep look into the cache. So if you see, like as you say, like initially when you are trying to request any of the web page or any of the heavy loaded application from the server, so first time it takes some time, right? Once it being loaded, so when the next time when you are trying to access the same page, then you will find it super fast, right? But you'll always not get all the content at same time, because there are some resources which are very much dynamic, right? For every request, that's a dynamic, and maybe if that particular resource is being updated in the server, then it might take a little more time comparing to the number of times you would try to access that particular page. So if you see, like in the past phase, whenever any request hits to the server, it's try to first hit to the cache, right? Then if that particular page or resource is not available in the cache itself, it will return one error code that should say 404 from the cache, but user cannot see that particular error code. So because browser handles that, so it will automatically send another request, same request internally to the actual server, okay, actual application server. So the application server will, or you can say the data store, so the data storage directly send the client as a response, right? So and the same response again will be stored into the cache itself, right? So whenever next time you will try to access the same resource, see at the third point, you will try to get the a resource from the cache itself, and the browser got 200, the success code. So now you are able to see the page. So next time whenever you are trying to hit the same page again and again, so this workflow will execute again and again, okay, as long as you are accessing the same page. The basic concept of any cache is the cache uses locality of reference principle, which is nothing but the recently requested data is likely to be requested again, right? So cache can be implemented in any or all level in the architecture that we'll discuss momentarily. Cache is like a short-term memory which has a limited amount of space, and it is typically faster than the original data source. When we're talking about the cache, though, I mean, cache may contain 3 different kind of data sets. So one is called pre-calculated result, right? So the cache always holds the pre-calculated data set for faster response to any repeated resources, as we already seen the previous slide, correct? For example, the number of clicks to a specific web URL, right? So if you are keep accessing a specific web page again and again and again, so maybe if you're if a browser having some statistics, feature, it will keep calculating those number of times you are hitting to a particular phase, then it will it's called the pre-calculated result, right? Then it always keep storing that in your system. So, and the other one is the pre-generating expensive indexes. So what cache is usually does is like cache keeps the history data once the resource access, right? So it will keep holding the history in the cache itself. So for example, the suggested products with user click history or browsing history on an e-commerce website or application, right? So let's, for example, you are trying to search some product in any e-commerce applications, I would say Amazon or eBay or any of the applications, right? So the moment you keep looking into other next products, you will have another section called the products you already you already visited or you already look into. So there you will see like all the products or all the items you have already visited in the whole system, right? So that's where the cache comes into picture, and it keeps storing those history and it keeps showing you in the system. So if you say there are billions of users using the same feature, so cache has to also make a have a mechanism to make it index for every user or every local or something like that, okay? So that it whenever user is accessing those data, they can really retrieve those data very fast, correct? And you can also take an example of a web browser, right? So if you go to the Chrome, Safari, or any of the web browsers, so there is a menu called history, right? So when you go to the history, so you'll have all these history of all the pages you have already visited, right? So if anytime your web browser crashes, then it asks to restore. So from where it's really restoring? It's really restoring from the browser cache itself, right? So there is a local cache available in every browser, so it comes from there. So if anytime you're going to clear that, then you will never get those, because you've already cleared those cache cache memory itself. So you will never get those history. So another thing is like it's storing the copies of any resource. So the cache really downloads and stores the heavy resource into the browser local for the high availability of the resources and the less network bandwidth consumption, right? For example, stores the copy of frequently asked data or resource like heavyweight images, graphics, and web pages, correct? So there are different caching mechanism any cache server to deal with. So it would say, I mean, as you said, like in our load balancer, we already saw like different kind of algorithm being used by the load balancer to identify any server to solve the request, correct? So likewise, cache also has the different mechanism to cache the data. So the first one is the cache aside model. So in this model, the requested data from the cache using a key. So always. So the first mechanism is the cache aside model. So in this model, the request data from the cache using a key. If cache has the data, return it to the caller immediately. If there is no data, we request the persistent storage for data. Okay, so after getting the data from the DB or database, we put it back in the cache with the key itself, right, and returns the data. We call this cache aside model. It is the default way of working with the cache for most applications. Like it's a simpler way of doing. I mean, using the cache mechanism. So the other mechanism is called read through cache. In read through cache, the application always requests data from the cache. If cache has no data, it's responsible to retrieve the data from the DB using an underlying provided plugin. After retrieving the data, the cache updates itself and returns the data to the calling application, right? And the third kind of mechanism is called a write through cache, right? As the name goes, right, the data is first written to the cache and then to the database. This ensures consistency between the data in the cache and the database, correct? So every read done on the cache follows the most recent write, correct? The other mechanism is write behind cache. This is variation of write through cache. Instead of fast return to the cache, and then to the database. So what does it mean is, like in the write through cache, what it does, it passed data being written to the cache and then database. But in write behind cache, instead of directly writing to the cache, it queues all the database updates, and then it update the whole batch at once. Okay, so that is the difference between the write to cache and the write behind cache. So there are common use cases where cache being used. So one is the database caching. So the cache layer in front of a database serves frequently accessed data in memory to cut down latency and unnecessary load on it, right? So there is no database bottleneck when the cache is implemented in front of the database itself. So that is one of the uses of the database caching. So the other one is the storing user sessions. So when any system trying to store any user session, and there also the caching can be leveraged. So user session are stored in the cache to avoid losing the user state in case any of the instances goes down, right? If any of the instances goes down, a new instance spins up, reads the user state from the cache, and continues the session without having the user notice anything amidst. Another kind of use case would be like cross-module communication and shared data, right? So if there are multiple modules available in the system, and if you want to communicate between those components, and that has to be seamless, then probably the cross-module communication and shared storage comes into picture, right? So in memory distributed caching is also used for a message communication between the different microservices running in conjunction with each other, right? So it shares the shared data, which is commonly accessed by all the services. It acts as a backbone of microservice communication. So distributed caching in specific use cases is often used NO-SQL data stores, and the other one is like in-memory data stream processing and analytics. So in this kind of use case, as opposed to the traditional way of storing data in batches and then running analytics on it, so in-memory data streaming processing involves processing data and running analytics on it as it's streamed in real time, right? So this is helpful in many situations such as anomaly detection, fraud monitoring, online gaming, create the stars in real time, so real-time recommendations, and also real-time payment processing. Let's see like how the cache can be used in different scenarios, different use cases, and different places, right? Like load balancer we have discussed earlier, the cache also can be placed all those places along with others. Cache can be used in different places. So one is the client side, right? So client side mostly is nothing but it's more specific to the browser. So how the browser implemented the caching mechanism. So it's for accelerating the retrieval of web content from the websites. So that deals with the HTTP cache headers and the browsers. Okay, the other one is the DNS. So the DNS is it's what it's used for domain to IP resolution, right? So it's mostly used for the DNS server to resolve the DNS very quickly and faster. So in our marketplace, you see like the in AWS services, AWS Route 53 is one of the mechanism where one of the service provided by the AWS Cloud to deal with the DNS system and also a caching mechanism. So the other one is the web server. So the caching can be used in the web server side of the house. To also helps to retrieve the web content and web apps very faster. The Redis and Memcache the tools available in the market can provide those facilities for the web servers. So it's also deals with the HTTP cache headers, CDNs, reverse proxies, web accelerators, and the key value stores. So the other one, application caching. So application caching is used for accelerate application performance and data access. So if any data, any data being used for multiple iterations or multiple calculations, maybe that can be cached in local, and the data can be stored in a key value way, right? So Redis and Memcache tools are also providing those kind of facilities and those kind of services. The other one is like the CDN. The CDN is also it really serves the static media of your application servers and provide a geographic distributions, right? So in your all video content distributions and all your, say, Netflix, Amazon Prime, or Hotstar, all those the content providers, they definitely use the CDN, and the CDN has its own caching mechanism, right? So it really helps to peer-to-peer CDN, push CDN and origin pull CDNs, right? So these kind of services provided by for example like AWS CloudFront and Cloudflare, and there are similar kind of services also available in our Google Cloud and the Azure Cloud as well. In database side, when the cache is being used, so it's for reduce the latency associated with database query and any kind of requests, right? So what it does is like any when user queries anything, so it really hits to the database, and it buffers the data retrieved from, and it stores as a key value store into the cache itself. So here also Redis and Memcache kind of tools provides those kind of mechanism. When we talk about cache, we talk about what are the what is cache and how it works, but how it works in a distributed system. So a distributed cache is a cache that has data spread across several nodes in a cluster, or across several clusters, or across several data centers, one or across the region. So distributed cache leverages the high availability and horizontal scalability, where the new instances are added as per the demand, and also it can be removed where it's not needed. Correct. So scalability, high availability, fault tolerance are crucial to the large scale services running online today. So business cannot afford to have their services go offline. Correct. So let's for example take example of Visa, right? So if any time the whole system goes down, so maybe the customers using the card, they're not able to process their transactions as quickly as possible, right? Or because till the time they'll not get any notification, they'll not get that transaction being processed or something like that, right? So they can't afford those kind of system. So think about health services, stock market, or military, right? So they have no scope of going down. They are distributed across multiple nodes with a pretty solid amount of redundancy. So these are the places where the distributed cache comes in picture. There are different use cases, as we say, like one is to isolate the application and to store the web session data, and of course decreasing the usage of network bandwidth and the cost as well. Correct. And reduces lots of other interruptions as well, because when you are not using any cache, so it will definitely try to again and again hit to the actual server, and it will try to get the data, and there might be other tasks, because it's all about a distributed system, right? So there are other components, other requests come into picture to interrupt the whole request. Correct. So that also being reduced by using the distributed cache. And of course, the scaling is one of the biggest benefit out there by using the distributed cache. So the cache eviction and invalidation. So why a system need this? Because of, to do two things: to prevent any stale data, and to cache only saving the most valuable data to the server. There must be a strategy implemented to remove the data from the cache and replace it with the one that has more probability to be accessed in the future. There are some of the eviction policies are adapted to solve the real world issues. So one of them is the TTL, right? Time to leave. Time to leave is the time that an object is stored in a caching system before it's deleted or refreshed, right? In the context of CDNs, right? So TTL typically refers to content caching, which is the process of storing a copy of your website resource. For example, let's say the images of prices, text, likewise on CDN proxies to improve page load speed and reduce origin server bandwidth consumption as well. In this context, so TTL governs the refresh rate of these copies, ideally ensuring that stale version of your content are not served to your website visitors. Other one is called LRU. So LRU is nothing but the least recently used, right? So so this kind of policy is a cache eviction strategy wherein if the cache size has reached the maximum allocated capacity, the least recently accessed objects in the cache will be evicted. So just imagine the Instagram storing celebrities photos in a cache, right? So the data access patterns of these followers are such that they are interested in the recent photos. Where the cache becomes full, so it will remove the photo that was accessed long time back, right? So that's what called, it will remove it will remove the resource from the cache which is least recently used. That means it has to deal with that timing. Other one is called LFU. So that is least frequency use. Least frequently used means like this kind of mechanism. It keeps tracks of the frequency or number of times a data item is accessed, right? In case of cache size crossing a given threshold, it will evict the entry with the lowest frequency, correct? That means it has to keep track of like which resource is used how many times, right? So the lowest number of times a particular resource is access will be evicted first, correct? So in the above example, we can say the Instagram example, the user might have viewed multiple photos, but some of them viewed multiple times, right? So when the cache eviction happens, it clears out the photos that viewed lowest number of times comparing to the other photos, correct? And the other kind of strategy or other kind of policy is being used is MRU, the most recently used, right? So it's very much contrast to the LFU, right? So in MRU, the most recently used entry is removed and preference is given to the older entries to persist in the cache, right? It's little bit a different kind of use case. So this strategy is exactly opposite to the LRU, right? So the most common strategy for cache invalidations. So as you say, like there are different policies. We already talked about, like these are the policies. So what are the most common strategies to invalidate the cache? So one is the expiration time. So where the application knows how long the data will be valid. After this time, the data should be removed from the cache using a cache miss in a subsequent request, correct? So the other one is the freshness caching verification, where the application executes a lightweight or determine if the data is still valid every time the data is retrieved, correct? So the downside of the alternative is that it produces some execution overhead. Like every time it has to check the lookup. And if so, the other kind of invalidation strategy would be like active application invalidation, where the application actively invalidates the data in the cache, normally when some state change in the cache identifier. So here is the storage. Other most important component is storage. So when it comes to storage, there are three very common questions always hits to the mind. Is like what exactly to store, right? And how to store and where to store. And when it comes to the cloud storage, there are four types of cloud storage can be leveraged. So one is the personal storage, private storage, public storage, and hybrid storage, right? So these are the different kind of storage in cloud. So there are mainly three kind of data we can store into a data. So what data can be stored? One is the file storage, right? So what is it? What is the file storage? So file storage means accessing single piece of data over the network, stored as file on a storage medium, right? To stay organized, one can build a hierarchy of folders inside other folder, which contains your files, correct? So depending on the specific variant of file storage, limitations such as access restrictions can be put on folders and files within the hierarchy, right? So how this file storage can be used? So file storage is based for data that is user defined. So where end users add, modify, delete the data, it's for data that needs to be very accessible and available quickly, right? So think that like PowerPoint presentations or Excel spreadsheets. Like file storage aims for price performance, right? So however, file storage does have usability limits, and because the information is so structured. Scaling means not just adding space, right, but adding new layer to a gigabyte systems, right? So you can only have so many folders within folders before get overly complex, right? Does the content of this file belong in folder X or in folder Y? So this system is good for maybe hundreds of thousands of files, or maybe even million of files, but not billions. So there is another kind of data can be stored is the block storage. What is block storage, right? So block storage is a very technical way of accessing file data, meant to be used by applications, but not exactly directly by people, right? So in simplest term, this storage type takes data and breaks apart into chunks of information of equal size that can be accessed directly, right? Instead of having to follow a path of folders within different folder like file storage, each block of files has its own address and contains pointers to the next block that belongs to the piece of data. Though as block storage is not meant for users to interact with, since the file's metadata that is built-in description of what the file is, how it should be associated with other files, and who can access it, can only be read by machines. This method is only as good as the server system it employs. So how it is used? So block storage presents the highest performance for accessing or consuming data. The type of performance required for database systems, which is the kind of environment where you will find it, right? In this kind of system, applications can work very quickly with block data to retrieve and modify information faster than any human code, right? So however, because of its performance characteristics, block storage is very far the most expensive way to approach storage, right? So the other one is the object storage. correct? So the a third option for the third option is object storage. It prioritizes efficiency and cost effectiveness. In this methodology, all pieces of data are tagged with metadata that includes a unique ID that describes the file's content and location. Once all the pieces have been marked as distinct objects, their addresses are as an object. Okay, a single entity in a big open pool of objects accessible from many many different locations at a time. To access the data, just use the ID or metadata associated with the object. Think of it like the junk drawer in your house that has a lot of useful things inside, but nothing organized in a meaningful way. So how does it work, or how does it being used? So operating like a library self, existing set pieces of information in object storage can be easily retrieved and used. However, the format is not meant to enable the editing and alteration of such information. So this means it's best of storing and retrieving largely static data. For example, a music MP3 file you want to listen to. The object stored itself is not usually accessed directly, right? It is presented through an interface that access the object store and its distributed data behind the scene, such as reading a ebook or with your e-reader, or watching a movie using your smartphone or smart television. Object storage is unstructured and low maintenance, so storing larger quantity of data is easy. To increase capacity, simply increasing the size of the warehouse or storage. So this agility and simplicity of design provide economic scaling that impacts the associated cost as well. So there are some of the consideration need to have, like out of all these three of storages, how you want to choose the best one, right? Honestly, there is no straightforward rule to choose one out of these three. However, it really depends on the use case you are really trying to solve. So let's talk about like what exactly this these are the criteria we can really take into consideration to choose a particular storage over any other storage type, right? So most organizations have processes, applications, workflows, and use cases for different type of cloud storage. If you want to truly maximize productivity and minimize cost, the answer isn't the answer is not only one of the storage solution outlined above, but it's all in the right combination, correct? So analyze the workload and applying the right type of storage for each one is the key. Choose a specific storage. So have a lot of email attachments that are accessed and shared by many people. You are probably looking file storage application. If you have a database or mail server, so sounds like you need a block storage solution. When you're looking to store a lot of historical financial backups for long term, then that's a job for object store. You need to analyze your environment to identify different type of solutions and match the appropriate storage offering to the correct purpose, right? So you have to take a decision like what is your use case and what kind of data you're trying to store and for what purpose. Okay, so that's how you need to take these take these strategies into consideration. One of the major part of the storage is scaling. So scaling, once the type of store being decided, the next most important thing must be taken into consideration is scaling the storage server, correct? So like load balancers and cache servers, the data store also data store servers also can be scaled vertically as well as horizontally. Also can be configured the data store for high availability to serve the peak loads. For data store performance, so the first is the indexing. So indexing the data based on the columns, and while there is indexing, so it can speed up the read performance. It's right. Writes are also make system slower, but more storage also required, right? While the indexing is really gives more benefit from the performance, also it takes some overhead, right? So, and denormalizing the data set we are storing into the data store, right? So one, it's really adds a redundant data to the to reduce join, boost read performance, but makes the whole system a little bit slower, right? Because it's denormalized whenever the data being written to the data store. First it has to denormalize and write the data, right? And the little complex coding and development required to meet the required use case. And the other one is the data replication. So by replicating data, the performance of the data store can be increased drastically, but yeah, so you have to build the read replicas, and data can be shared for the multiple applications, multiple services, and data partitioning, so there are different kind of data stores available in the marketplace. One is a SQL type and the other one is NO-SQL type, right? There are some of the services available out there in the marketplace to use for different use cases. Can a NO-SQL be used for all kind of use cases or vice versa? The answer is of course no. I would say one size doesn't fit all. Correct. So since NO-SQL data store don't really support the ACD rule, right? ACD rule or ACD properties in favor of the scalability and performance. So where the cap theorem comes into picture. So we will talk about the cap theorem in a different session altogether. But yeah, these are the tools and techniques and services available in the market where the cloud providers really provides those and as a managed service. Yeah, so those were all about the data store, and we'll now talk about the message queue. This is one of the most important component, the pillar for the whole system design. Okay, so the message queue. In simple words, a message queue is a messaging system that uses the queue data structure to facilitate asynchronous communication between two services, right? So the areas we are going to touch upon are like what are message queues, components of a message queue, different properties of a message queue, message queue architecture in nutshell, and how the architecture works, benefits of using message queues, and message queue high availability, right? So, but I would highly encourage to visit one of my previous video published, the topic related to hyperscale application design and architecture pattern. You can see the link to the video. It's flashing on the top of right of the screen. So what are the message queues, right? The message queue is a messaging destination that uses the queue data structure to facilitate asynchronous communication between two services, right? So they are commonly used in serverless and microservice architecture design pattern. The message queue is comprised of two components. One is the message and the other one is the queue. So message is the data that is passed from the producer to the consumer. The data can be in form of request, information, metadata, etc. Right? So in other side, the queue is a temporary buffer that stores messages it uses the fast in fast out methodology to pass the messages from producer to the consumer. So what are the different properties of any message queue, right? So message queues are asynchronous in nature. So this enables the producer to send any number of messages and continue with other tasks without waiting for a response from the consumer, correct? So once the consumer processes the message, it can then notify the producer. The message queues temporarily store messages until they are received and processed by the consumer. Each message is processed only once by a single consumer, even though the message queue can be used by many producers and consumers, right? And definitely not necessarily like only once, but it's all about the configuration of the consumer and how you have written the consumer to consume the data from the events from the message queue itself. So if you see like what are the different anatomy of the message, any message queue, so it comes with four different components. So one is definitely we talk about the message, and the other one is the queue, and the most important users of the message queue are the producers and the consumers, right? So producer uses the queue to publish the data or event, and consumer uses the queue to retrieve the data, retrieve the event from the queue itself. The message queues increase the reliability of system as the processed data in case some part of the system goes offline, right? So that's how it also help to keep the whole application live. The improved performance is the enable asynchronous communication. So this ensures that every system component is never idle or waiting for a response or request, right? So message queue increases scalability as the system component are decoupled and thus can be independently scaled. This is an illustration of a message queue architecture, how the message queue architecture looks like. So in high level, the message queue architecture is made up of producers and consumers and the brokers, correct? So producer, it acts as a client application that creates and sends the message into the queue. The consumer is service that acts as a receiver, which receives and processes the message from the queue itself. How this architecture really works: the producer creates the message and sends it to the message queue. In case the consumer is busy to immediately process it, the queue stores it until the consumer is available, or the message is valid and still stays in the queue till the retention policy configured for that particular queue, right? The consumer retrieves the message from the queue and starts processing it, and the message queue then temporarily locks the message to prevent it from being read by another consumer. So after the consumer completes the message processing, it deletes the message from the queue to prevent it from being read by other consumers. But definitely not. This is not true for all. Okay, for all, because if you want to retain the data to use by other consumer groups or consumers, you can just keep increasing the offsets offsets in the queue and keep going. You don't the consumer really doesn't have to delete the event from the queue, and it's not a ideal way of dealing with the data in queue. Rather, you need to have some indexing mechanism in the queue itself. You just need to make it a flag read. So that's those kind of mechanism already provided by Kafka kind of system queue, where they are already using the offset of a message to make it read offset. So how to make a message queue or highly available? It's never been an easy to build a highly available message queue in the distributed system. However, these are some of the most important points need to be considered while building and deploying such a system. Correct. So the high availability can be achieved by adding the backup broker to the primary broker. So this can be achieved using the quorum technique, like 2n+1 number of brokers in the cluster. Correct. So we will talk about quorum little bit more in depth in a different session. So publishers and consumers can independently specify their quality of service, that's called QoS, direct or persistent. So clients establish connections only to the active, that's called the primary broker. There is no need to create or monitor multiple connections for a single client. Okay. And need to maintain a clean and simple failover strategy. Or whenever the primary broker fails, the backup broker seamlessly switches its status from the standby to the active broker, allowing clients to automatically reconnect to the active broker itself, right? So that user will not really experiencing any system downtime or something like that. So persistent messages should be automatically synchronized between the active and standby brokers before sending an acknowledgement to the publisher. There should absolutely no message loss, right? So that's the most important feature has to be there when it's the high availability comes into picture. So once the failed broker comes back online, message reconcile should happen in the background and automatically for persistence message as well. Right. So there should be a monitor broker considered to avoid split brain scenario. So the split brain scenario is another concept and topic we need to talk about later. So the message order should be also preserved across all consumers regardless of their regardless of their quality of services. These are things need to take into consideration when you're building a message queue for the high availability or high available message queue. So APIs are all over throughout the system design landscape. Okay, so and this is very important component in this system design landscape to interact between multiple components and multiple servers or multiple workflows. So API design refers to the process of developing application programming interfaces, that's in short calls APIs, that exposes data and application functionality for use by developers and users as well. So APIs are important to modern organizations, adding new capabilities to everything from their operations and products to their partnership strategies, right? So it's no longer a stress to say that most organizations don't ask whether to engage in API programs, but not how to do so. This, I just wanted to touch upon, like in this screen itself, you see like user is, request to the load balancer and the request to the web browser, and there are some, multiple APIs available in between the web server and the application server or cache or database server, right? So these are the places where the APIs, it's a first place where the APIs can be incorporated to access to other system in the whole system of the product. So the APIs can be placed at different points of the product landscape. Here are the four important and commonly used areas where the APIs are really important, right? So one is the information management layer, the other one is the application layer, and integration layer and interaction layer, right? So the information management layer is where you, in your throughout the system, you have some metadata, some kind of core data available in your system where you want to deal with that day to day, right? Or maybe other applications need to be deal with those metadata system, right? So that's where there is set of APIs really needed to interact with those kind of information and manage those information as well, correct? So the other one is the application layer. In the application layer, so let's, for example, there is a microservice running on the system, and that microservice it is really generating lots of matrices related to the load, related to the number of tasks running, and number of concurrence process really running under that. It's just for example, right? So how can you really deal with those? How can you, if you want to build a dashboard on top of that to really monitor those things, then how you'll deal with that? So you have to really build some set of APIs which will really take care of those kind of information, those kind of details to retrieve from the application itself. So that comes into the application layer information. Other layer would be the integration, right? So there are multiple pieces of the whole system design, and if you want to integrate between all these components, then there has to be some medium of communication where they can really interact each other. So that's what called the integration layer. So the API is the only way to deal with those kind of system and interacting or handshaking, right? And the interaction layer is also kind of the layer where you want to do some crowd operations, kind of like, okay, you want to update some configuration, you want to retrieve some configuration, and maybe you need to clean up some configuration. Those kind of work and functionalities probably for every system need. So this is the layer where the APIs also come into play. So why do we want to implement APIs? So that's where we already talk about that, right? So different layers need different kind of APIs to really deal with the different kind of use cases. So people often misinterpret this question, like why we really want to implement APIs, but firstly, rather than focus on the value of the API, it's helpful to think of the value of the effect of the API, right? Remember, it's the organization's core business that's valuable, not necessarily the API. An API is valuable when it becomes a channel that provides new type of access to the existing value an organization delivers, correct? So another common misconception is believing that for an API to be valuable, users must be prepared to pay for it, right? So it's always not true, correct? So this is true only if the API itself is the product. Okay, itself is the product. In most model, this is not the case. APIs are usually driving some other metrics else, and affiliate referrals or brand awarenesses, or all those things, right? So the value of the API to users is, so the top technology drivers are to improve application integration, improve mobile integration, and support the connection to more devices, right? So the benefits to the organization need to be strong enough to make the decision to invest in the APIs and obvious choice for the organization. Team level questionnaires or the API level questionnaires need to be clarified before jumping into that. Here are the couple of points one should take into consideration while building an API. The best practices would be like use throttling whenever developing any API, enforce API gateway to secure your APIs, and allow overriding the HTTP method, evaluate the APIs and infrastructure, and ensure the utmost security, and of course proper documentation for all those APIs you have, right? And whenever you're designing any API, you need to really understand the in and out, right? In and out means what you are really looking for, and what you are sending the data to the actual server through that API, and what you are expecting. That need to be very clear enough for the user when it comes to the usability. So the last but not the least, the most important component is security. Security is all over, like our APIs, the security is all over. So in every stage or every component in the service or module available in the whole system design, really need a security, some kind of security, right? So security is a strategy pull off to protect the resources connected to the corporate network, right? So each resource, when connected to or from remote, creates a potential entry for security threat, right? While enterprises embracing a new technologies to meet business demands has opened doors to cyber attacks or security compromises, right? So if you see in the screenshot itself, here are some examples how the security plays crucial roles in different places and different situations and environments to provide utmost shield to the system. So if we think of like if this is a whole system design landscape, and this is the whole infrastructure we have, then when the internet, any user try to access to the system through the internet, it comes to the first the DNS and applies the security over here, right? And then it's try to connect to the gateway, and there is a security applied. And when that request come from moves from the application gateway to the actual applications, it might be a web application or the app server or any other applications or load balancer, any kind of other components available for the front end execution. So in between that also there is a security applied that's called NSC, right? And when any request goes through the web app to the actual backend service or the middleware service, so there also the security can be applied. So in every layer, wherever the layer we are able to we have been putting the load balancer, we have been putting that and those kind of components to really make the whole product performant. So in those places we can also provide the implement the security system altogether to make the whole system completely secure, right? So that's where the whole how the security comes into play, and how it's really gives the benefit out there to the whole outside world. As we know, the security is all over. There are different areas where the security always comes first. The network security, cloud security, mobile security, IoT, app security, whenever you are uploading any apps or building any applications. So there also the security comes into picture, and the data side of the house. And when it comes to the computing, and nowadays we have a different kind of application execution, like, so one is the storage and compute, right? So when any application running on the compute side of the house, it's try to access the data from the storage, right? It might be the internal or external storage. So that need to be that also in that place the security also need to be considered, correct? Otherwise there might be a data mesh, or there might be a security breach in the phase of transitioning the data between the storage and the computation, correct? And the computation level itself also, there might be some other factors which really compromises the privacy of data. There are multiple ways where policies can be created and enforced. So to ensure the maximum security, here are some of the policies can be ensured. One is the user or application with control operations, right? So, and the other one is the applying the confidentiality and integrity and the availability of the system, and applying the authentication service where it tells like who actually can see what kind of resources, right? And the authorization, who can modify or invoke the data, correct? And once these policies can be ensured, like how those can be enforced, right? So creating policies cannot be just enough unless it's enforced for the system, right? So that can be enforced by passing or blocking some of the traffic or all of the traffic to the system, or applying enforcing some mechanism like accepting or declining some of the requests according to the HTTP headers, or according to some of the other criterias, if that doesn't meet to the policy. And permitting or shutting down the executables, there might be some malicious executables coming into the system, where that might create lots of security threats, right? So somehow whatever the policy defined for those kind of things, so that need to be enforced by either permit the executable, or maybe need to be shut down or just kill it, right? And the other one is the encrypt traffic or data, right? So whenever the traffic comes in the system or going out of the system, so the encryption need to be applied to the complete traffic, so that it cannot be deciphered in the middle of the transition, correct? And the data also need to be encrypted, so that the data security will be always enforced. And the isolate users or applications. So what does that mean is like, okay, so user, whenever any user any user trying to access to the system, so the user need to be need to be segregated properly, and need to be control over all the resources it's available in the system landscape, right? So even it may be a human human to machine, or maybe machine to machine interaction, but they have to be isolated from each other, right, to ensure utmost security. And there might be some others as well, but yeah, these are the most important policies and enforcements can be taken into considerations. So for the security, there are lots and lots of tools and services available in the marketplace. And if we'll just talk about some of the example from the AWS cloud provider, so there are 3 types of securities can be implemented throughout the system design, right? So one is the identity and access management, right? So which really talks about the there are actually segregated in 3 categories, right? So one is identity protection, so other one would be the infrastructure protection, and the third one is the data protection, correct? So And if we think of AWS cloud, there are a bunch of security services available for different use cases. Like if we talk about the how can we enforce or implement the identity protection. So for that, so there is a managed service called Identity and Access Manager, right? The IAM service, managed service. So which is being provided, I mean, through multiple services that's called AWS Cognito, AWS Single Sign-On, AWS Directory Service, and Resource Access Manager. And for the infrastructure protection, so there are some services which is available for AWS Shield, AWS Firewall Manager, AWS Web App Firewalls, those kind of services. And for data protection, you see like Amazon Message, right? And Amazon Key Management Service, the KMS, and the Amazon Cloud HSM. That's really really moreover related to the hardware security module. And the other one is the certificate manager model, right? So those are the tools and services really provided by one of the big player in this cloud game, the AWS. So this is just example, and the similar kind of also services available in our Google Cloud as well as the Azure Cloud, right? So I mean, not necessarily, I mean, this has to be incorporated to ensure the security, but there are also a lot of open source services or open source tools that can be leveraged to or deal with this security system. So so as we have already discussed, I mean, all 6 major components and the pillars of any system design, these are all 6 most crucial pillars of any system design everyone need in their day-to-day work while designing and architecting any large-scale system. Okay, so hope this session fulfill everyone's expectation. Thank you for your patience listening me the whole session. Please give a thumbs up if you like it, and don't forget to subscribe if you haven't yet, to get notified for any upcoming sessions and videos. So and yeah, have a great one and stay safe.